Today we're looking at a class of materials that, well, it almost feels like they're pulled straight out of science fiction. We're not talking about simple elements here. These are high-performance, engineered hybrids built layer by layer for a kind of strength that's just unparalleled. We're talking about composites. And in this explainer, we're going to break down exactly how these remarkable materials are put together, piece by piece. But what if I told you we could engineer a material that just breaks the traditional rules? Something that completely defies the usual trade-offs you have to make between weight and strength. A material that is somehow both lighter than aluminum and, at the very same time, significantly stronger than steel. I mean, does that even sound possible? It is, and they are all around us. Meet composites, the silent superstars of modern engineering. You'll find them everywhere from the wings of our most advanced jets to the chassis of a Formula One race car. These materials have completely redefined what we even think of as high performance. So what are they, really? How in the world do you create something with properties that seem to contradict each other? Well, it all starts by understanding that composites are, at their heart, the ultimate hybrid. Now, the core definition is actually surprisingly simple. A composite is really just a combination of at least two different materials that don't blend or dissolve into each other. No, instead, they work together. Each component keeps its own identity, but contributes to creating a powerful new whole. The recipe is actually pretty elegant. First, you start with a matrix. Think of it as the glue, often a polymer resin like epoxy. Then, you introduce the reinforcement, and this is where the magic happens. We're talking incredibly strong but lightweight fibers, like carbon or glass. When you combine them, the matrix holds the fibers in place and transfers the load, while the fibers, they provide that immense strength and stiffness. The end result is a material that is so much greater than the sum of its parts. And, while they feel so futuristic, the basic idea isn't new at all. Humanity's been using composites for centuries. To really get a grasp on their impact, we need to look back at these key moments where these materials didn't just improve technology, they completely changed the game. And this wasn't some gradual evolution. We're talking about a history of huge, disruptive leaps. Back in the 1940s, the de Havilland Mosquito, built from a wood composite of all things, outran its metal counterparts. Then, you fast forward to the 80s, and Formula One was changed forever when McLaren built a car around a carbon fiber tub, making it unbelievably light, rigid, and safe. And then, in the 2010s, commercial aviation was transformed by the Boeing 787. And what's so amazing about the Dreamliner is the sheer scale of that change. The aircraft is about 50% composite material by weight. Now, that's not just a few small panels. That's the fuselage, the wings, the very core of the aircraft. This wasn't just some small upgrade. It was a revolution that led to a massive 20% gain in fuel efficiency. Just incredible. That kind of leap in performance really makes you wonder, what are the superpowers that let composites dominate in these extreme situations? Why do engineers turn to them when absolutely nothing else will do the job? Well, it all starts with one truly staggering number: 7. High-grade carbon fiber composites can have a strength-to-weight ratio up to 7 times that of steel. Just let that sink in for a moment. All the strength, it's just a fraction of the weight. This right here, this is the property that changes everything. But the advantages go way beyond just strength to weight. I mean, unlike metals, they don't rust. They're incredibly resistant to corrosion and fatigue. They're also brilliant at damping vibrations, which makes for a quieter, smoother ride. And maybe their cleverest trick is something engineers call anisotropic, which just means you can literally design their strength in specific directions. You can reinforce a part exactly where the stress is highest and save weight everywhere else. It's brilliant. Okay, so if these materials are so incredible, why isn't everything made from them? Well, it turns out every superpower has its weakness. And for composites, the cost of all that amazing performance is incredibly high. The single biggest thing holding composites back from taking over the world really comes down to one number: 20. A part made from carbon fiber can cost up to 20 times more than the exact same part made from steel. That's a premium that you can really only justify in the most demanding, high-stakes applications. And cost isn't the only problem. The manufacturing process itself is slow and complex, requiring a lot of skilled labor. And if they do get damaged, repairs need specialized expertise. You can't just weld them like you would a piece of steel. Then there's the environmental issue. Many composites are notoriously difficult to recycle, which creates a real end-of-life problem. And finally, their power does have limits. They generally just can't handle the extreme temperatures you'd find inside a jet engine. And this quote just captures the central trade-off perfectly. Composites really are the supercars of the material world. They offer breathtaking performance that nothing else can even touch, but they're expensive, they're finicky, and they're just not built for the everyday commutes. Amazing, for sure, but definitely not for everyone. So with all these incredible strengths and these pretty significant weaknesses, where do composites actually land on our ranking scale? It's time to weigh all the evidence and deliver the final verdict. All right, looking at the report card here, this story becomes pretty clear. Their mechanical properties, nearly perfect, a 9.5. Their historical impact and lasting relevance are also incredibly high, an 8.5 and a 9, because they're so central to green energy and aerospace. But then, look at the scores for scalability and cost, a 6, and workability, a 7. This is exactly where that supercar analogy really hits home. So when you tally it all up, composites land firmly in the high A tier. They are true performance legends, absolutely irreplaceable in the niches where they dominate. But those serious drawbacks in cost, in manufacturing, and in recycling, they keep them from reaching that universal, world-changing status of an S-tier material. To put that into perspective, just think about steel, a true S-tier material. Steel is the universal workhorse. It's cheap, it's scalable, it's versatile. Composites, on the other hand, are the specialists. They don't even try to compete with steel everywhere. No, instead, they win where performance is the only thing that matters. And you can see that specialization playing out right here. A full 40% of advanced composites go into aerospace. Another 25% goes into building those massive wind turbine blades. These are industries where shaving off a little weight or adding a little more strength provides an absolutely enormous return on investment. And what this all tells us is that composites aren't just some historical curiosity. They are absolutely essential to our future. Lighter planes mean huge savings in fuel and carbon emissions. Longer, stronger wind blades generate more clean energy. And making things lighter is critical for extending the range of electric vehicles. They're a key technology for building a more sustainable world. Which leaves us with one final lingering question. Composites truly are the material of tomorrow, and they're available to us today. They allow us to achieve things that were once flat out impossible. But as we build more and more of our future with them, from wind farms to electric fleets, the clock is ticking. Can we solve their fundamental recycling problem before the wonder material of today becomes the waste problem of tomorrow?